Good afternoon, everyone. Thank you for giving me the opportunity to present the crystallization webinars. My name is Panayiotis from the University of Leeds, School of Food Science and Nutrition, and today I'm going to present my work on the bulk chemistry and physiochemical properties of different structures of quercetin using molecular modeling and experimental studies. And I'm going to start off by giving some background on solvates, then move to the methodology of the molecular modeling experimental validation, the results, and some conclusions and future developments. And we all know that crystallization is a process of solid formation, which results in a 3D structure which is characterized by a long-range order. And solvates are multi-component crystalline solids which contain both the host molecule. So in this case, the host molecule is quercetin, and solvent molecules. And specifically, when the solvent molecule is water, these solvates are termed as hydrates. And you can see the water molecules which form part of the structure of the quercetin dihydrate in this figure. And the solvate molecules in the lattice can form interactions with with the host molecule, for example, hydrogen bonds. And these can affect the physiochemical properties, for example, the solubility, the surface chemistry, the stability, and the bioavailability. And solvate structures are particularly attractive for the pharmaceutical and the food industry because they can be exploited to manipulate some of the physiochemical properties and actually get desired properties, for example, as I mentioned, solubility. So for this reason, it's really important to be able to study these structures and understand them so that to avoid any unexpected transformations, for example, whether the stability is concerned at any process during at any stage during the processing of the crystal. Quercetin is a naturally occurring flavonoid substance. It is found in many red fruits and vegetables, and it is widely used in the nutraceutical and food industry because it has a range of health benefits. For example, it is an anti-inflammatory agent and an antioxidant agent. And it can exist as an anhydrous structure, a monohydrate, a dihydrate, and a DMSO solvate. And as I said earlier, it is really important to be able to study those structures. So while experimental studies could be time-consuming and expensive, molecular modeling can provide another route to study these structures by calculating the intermolecular interactions within the different crystal structures and using that information to explain some of the physiochemical properties and ultimately be in a position to predict some of the physiochemical properties as well. And this requires crystallographic information, which we obtain from X-ray diffraction data. So in this work, the aims were to use molecular modeling to study the bulk intrinsic synthons, which are the intermolecular interactions of the different quercetin structures, and use that information to predict some of the physiochemical properties, specifically stability, thermal stability, and also understand why the molecules take a specific path to the crystal structure. And also understand how the presence and the type of solvent molecules, whether that is water or DMSO, can affect the structure, the packing, and the conformation, and be in a position to explain those physiochemical properties. And lastly, we use some experimental techniques to validate the molecular modeling work. So for the molecular modeling methodology, I have been using a software called Habit 98. It is developed in the University of Leeds, and it is a syntonic modeling tool. And basically what it does is that it builds a series of unit cells in 3 dimensions, and it calculates the intermolecular, it calculates the strength, the directivity, and the dispersive nature of the intermolecular interactions between the central unit cell and all the other molecules within a sphere of 30 angstroms around that central unit cell. I've used CCDC Mercury software for the visualization of the intermolecular interactions, And for the anhydrous, monohydrate, and dihydrate structures, I have downloaded the crystallographic information files from the CSV, while for the DMSO solvate, that's a structure that was solved by our group, and the zip file was obtained from single crystal XRD. And for the experimental techniques, specifically for the thermal stability, I've used variable temperature powder X-ray diffraction and thermogravimetric analysis with differential scanning calorimetry. So what we see here are the results of the syntonic modeling, and the quercetin molecule can crystallize into a quercetin anhydrous structure, which doesn't contain any solvent molecules in the lattice. And it was found that for this structure, the strongest intermolecular interactions are hydrogen bonds and polar interactions, which are formed only between the different quercetin molecules, since there are no solvent molecules. And the conformation of the quercetin molecule was also studied, and specifically the torsion angle between the phenyl ring and the pyrrole ring of the quercetin molecule was calculated, and this was found to be 32 degrees for the quercetin molecule in the anhydrous structure, which means that the quercetin molecule is less planar, and for this reason, no pi-pi stacking interactions were observed in this structure due to the less planar conformation of the quercetin molecule. With one water molecule per quercetin molecule, we get the quercetin monohydrate structure. And it was found that the strongest intermolecular interaction in this form was a pi-pi stacking interaction formed between different quercetin molecules, which allows them to form stacks of pi-pi of quercetin molecules which interact by pi-pi stacking interactions. Also, the torsion angle was found to be 1.3 degrees, which means that the quercetin molecule is planar, and this planar conformation is what allows the quercetin molecules to form those pi-pi stacking interactions. As far as hydrogen bonding is concerned, hydrogen bonds were found to be formed both between the quercetin molecules and also between quercetin and water molecules. And with two water molecules per quercetin molecule, we get the quercetin dihydrate structure. Again, the pi-pi stacking interaction was found to be the strongest interaction in this form. However, the difference between the monohydrate is that in the dihydrate form, the pi-pi stacking interaction dominates the lattice energy. It contributes to 38% of the total lattice energy. And it was also found that hydrogen bonds in the dihydrate form only form between quercetin and water molecules. Therefore, we found that we can summarize this by saying that as the degree of hydration increases, the hydrogen bonding is preferentially satisfied by interaction with the water molecules in the lattice, which leave the quercetin molecules more planar, since the quercetin molecules don't need to twist in order to facilitate interaction between them, the hydrogen bonding between them. So this more planar conformation allows them to form pi-pi stacking interactions. So the contribution of pi-pi stacking interactions also increases with increasing degree of hydration. And also the stability of the quercetin dihydrate form was predicted to be with a higher relative stability, because there's a smaller amount of dissolvation needed and conformational rearrangement when it is crystallized from an aqueous solvent. And lastly, the quercetin molecule can crystallize into a novel structure from a 70% DMSO and 30% water by weight solvent. And the new structure is a quercetin DMSO solvate, which contains 2 molecules of quercetin and 3 molecules of DMSO in the asymmetric unit. And the strongest interactions in this structure were found to be several pi-pi stacking interactions, which is different to the dihydrate and monohydrate form, because we only got one type of pi-pi stacking interaction in the 2 hydrates. and also hydrogen bonding between quercetin molecules and between quercetin and DMSO molecules. And it was found that the torsion angle was 31 degrees. And this means that it is less closely packed compared to the other two hydrates. And this higher torsion angle can be explained because of the bulkier size of the DMSO molecule. And because in the two hydrate structures, the water molecule can position itself around the hydroxyl groups of the quercetin molecule and satisfy the hydrogen bonding. In the DMSO solvate, since the DMSO molecules are more bulkier and all the hydrogen bonding cannot be satisfied just by interaction with the solvent molecules, the quercetin molecule needs to form this torsion in order to form hydrogen bonds also between the quercetin molecules, and in order to facilitate those interactions, this higher torsion angle is assumed. And it is also interesting to notice that there was a higher contribution of quercetin and solvent interactions of 45%, and also that was high for the dihydrate forms, 46%, so the total lattice energy. And this highlights how the quercetin and solvent interactions are so important for the stabilization of the lattice for those two forms, the dihydrate and the DMSO solvate forms. Furthermore, the quercetin, the hydrogen bonds and the dipole-dipole interactions in the QDMSO form were found to contribute much more to the total lattice energy, around 40%, compared to the other forms. And also the hydrogen bonds in the QDMSO form were found to be stronger in energy compared to the quercetin solvent interactions in the hydrates, in the monohydrate and the dihydrate form. Now, moving to the experimental validation, I should mention that experimental validation was only performed for the dihydrate and the QDMSO solvate, because those two forms are the thermodynamically stable forms that we could obtain in the lab, whereas the anhydrous and the monohydrate, we couldn't obtain pure forms of those two. And that also highlights the lower stability of those two forms. So here you can see the DSC and TNGA results for the dihydrogen and QDMSO, and the first event that you can that we can see here is the desolvation of the two forms. And for the dihydrate, this happens at 95 degrees, whereas for the QDMSO, it takes place at a much higher temperature of 136 degrees. And this indicates that QDMSO is more heat stable, it's more thermally stable compared to the dihydrate. And from the TNGA curve, we obtain the observed weight loss for the dihydrate and for the QDMSO matches with the theoretical weight loss. So it indicates that this event is indeed the dehydration or desolvation for each structure. It's also interesting to notice that while for the dihydrate, the loss of the two water molecules occurs in a single step, as shown by the single endotherm here. For the QDMSO solvate, we observe a shoulder at a bit higher temperature, which could mean that the DMSO solvent molecules are lost in consecutive steps and not just in one step. And melting and decomposition temperatures occur at very similar temperature for both the dihydrate and the QDMSO, and also match with the melting and decomposition temperatures for quercetin compared to literature. Looking now at the variable temperature powder X-ray diffractions of the two spectra, for the dihydrate form, we can see that between 25 degrees and 70 degrees, we get the same spectrum, which agrees for the dihydrate form, while at 100 degrees, we start seeing some peaks decreasing in intensity, and some others disappearing or appearing, which indicates this phase transformation at the temperature of 100 degrees. And this temperature agrees with the DSC and TNGA data to be the dehydration temperature for the dihydrate form. And for the QDMSO, the structure appears to be stable between 35 degrees and 120, at which temperature we start seeing some peaks disappearing and others appearing, which indicates this phase transition at 120 degrees, which should be the dissolution comparing with the DSCN TNGA results. And what is also interesting to notice is that the final products that we get after dissolution of both forms, starting either from the dihydrate or the QDMSO, are identical. So this final form and the final form from the dihydrate are identical. If we compare the peaks, they appear to be the same. So from that, we can infer that both structures, after losing the solvent molecules, they dissolvate to the same pure form of quercetin. And both the variable temperature XRD and the DSC TNGA results show that QDMSO has a higher thermal stability compared to the dihydrate form. And if we use the molecular modeling results earlier on, we can explain that because of the stronger hydrogen bonds that the QDMSO structure, that the molecules in the QDMSO structure form. And basically this means that in order to dissolvate the structure, a higher amount of energy needs to go into the structure to break the stronger hydrogen bonds between the quercetin molecules and the solvent molecules. Therefore, this happens at a higher temperature. So in conclusion, we can say that hydrogen bonding is observed in all structures, and it is probably the first interaction to be satisfied during crystallization. And as the degree of hydration increases, this hydrogen bonding is preferentially satisfied by interaction with water molecules. And this leaves the quercetin molecules more planar to form pi-pi stacking interactions, for which the contribution also increases with increasing degree of hydration. And experimental validation has shown that the DMSO solvate has a higher thermal stability compared to the other thermodynamically stable form, the dihydrate, and this was explained because of the higher contribution and stronger hydrogen bonding in that form. And this work demonstrates that syntonic modeling can be a powerful tool which can be used to relate the crystal structure to the product properties, and can also be used at an early stage of solvate screening to differentiate between different solvate forms, and this can also lead to more efficient product formulation and faster development. And future work involves experimental validation of the surface chemistry of the different forms. The modeling work has already been done, unfortunately not shown in this presentation. So surface chemistry, the study of the surface chemistry of the forms is the next step in this work. Part of these results are already published, and it can be found online. And I would like to thank my supervisors, Dr. Elena Simone and Professor Megan Povey, and also Dr. Ian Rosebottom for his valuable help with the molecular modeling, and of course the School of Food Science and Nutrition for the funding of this project. And also thank you for your attention.
Thanks, Panayiotis.
Thank you.
Sophie, is there time to read one question, or?
Yeah, let's go ahead with some questions. I think some have come in the chat box.
Yeah, I think Jo from Leeds, she's asking if the model consider CH-pi interactions.
So let me just find the question. Or can you please repeat the question? If the model
consider CH-pi interactions?
So the way that the contribution was calculated was the interaction of the aromatic rings, which contains the aromatic carbons and aromatic hydrogens. CH-pi interactions question. So it involves the hydrogen, the aromatic hydrogens as well. Yes.
Okay. And Davide is asking, how do you quantify the strength of different interaction? how can you say that a pi-pi is stronger than a hydrogen bond?
So when we calculate the intermolecular interactions, those are ordered in terms of energy. We know we also get a polar component of the interaction and a van der Waals component, so we can differentiate between a more polar and a less polar interaction. So for the less polar interactions, which are the pi-pi stacking interactions, we get the energy of interactions, and that's how we can say if it's stronger or weaker. It has to do with the energy.
Okay, we've got then Tom Hardcastle is asking why do we use the Momani force field, as it doesn't really distinguish between carbon hybridization states.
So the specific force field was used because it has been shown previously to work well with organic systems that contain hydrogen bonding, and that's the reason that we chose the specific force field.
And the final question is, so we did do the dissolution of the dihydrogen and the DMSO. So they are asking if the powder pattern matched the anhydrous crystal structure.
Okay, that's a good question, and I should have mentioned that in the presentation. It was found that the anhydrous, the pure form of quercetin, starting from both the dihydrate form and the QDMSO form, did not match the quercetin anhydrous pattern of the quercetin anhydrous structure that we have modeled. So it could possibly be a different polymorph of pure quercetin. Unfortunately, we haven't managed to solve that structure yet because crystals of sufficient size could not be obtained. But it's not the same structure that it is deposited in CSD.
Yeah, Panayiotis has a paper coming out on that, by the way. So maybe you can check that as well. Okay, is there any more question, or maybe we go to Shangwen?
I've got a question that's a bit. I'm just curious. At the end of your presentation, you mentioned you're going to look at the surface chemistry.
Yes.
By what method are you planning on doing that?
So we are using the attachment energy model, and we are calculating the interactions that form on the outside on every surface of the crystal, and the solvent and then solute molecules which could be added to that phase. And depending on the interactions that are formed on the surface of each of the phases of the crystal, depending on the polarity of those interactions, whether they are hydrogen bonds or whether that phase goes by pi-pi stacking interactions, and in a way assign a polarity to each of the phases. And also it will be a prediction for the hydrophobicity of every phase as well.
Yeah, I think my question was more towards experimentally how you're going to measure that. Because
okay, experimentally we're exploring different techniques. Inverse gas chromatography is one of the techniques, although that one is more of a bulk characterization. AFM is another one, which hopefully will be able to use to study the surface chemistry. So measuring
sorry, just because we're out of time. I was wondering if you had a look at the Bragg Center and what equipment they have there, because the Schroeder group's got access to a pretty good XPS that they've been doing some surface chemistry analysis with, and that is just down the road in Leeds.
I've tried to use XPS. There's an XPS in chemical engineering in the University of Leeds. I've done some work, although very preliminary work, using the XPS. But if I'm not wrong, that the XPS can only calculate the elemental composition of the surface. I think so. I'm not sure if that can relate to the polarity of the phase.
Have a chat with Schroeder's group, because they've been doing some interesting stuff at the moment. That I think might be some overlap there with the surface chemistry.
Okay, okay. Thanks. Thank you very much for the recommendation.
No, it's good presentation, by the way. It's very good.
Thank you very much.
Thanks so much, Panayiotis. Was there any other questions? I think we've got enough people that you could open up your mic and speak if you have any questions.
I think Martin Ward was suggesting to look at the desolvated sample collected with XRPD and then try and at least index the patterns. Is that to solve the structure? Is that what you mean, Martin?
I think you're on mute at the moment, Martin.
If it is a new phase or not.
So the PXRD pattern that we get from the final product after desolvation didn't match with any other quercetin pattern that we obtained. So, and it didn't match with the quercetin anhydrous pattern from the seed file, which is deposited on CSD. So it could possibly be a new phase. However, we didn't manage to solve that one because of the size of the crystals. I'm not sure if that is what you mean.
I think it was just asking confirmation that it's actually a new phase than anhydrous that we get.
Yes, it is a new phase because it's definitely a phase which does not contain any solvent as shown from the DSC-TGA data, because there's no other loss in mass before the decomposition. So the form that we get after the desolvation of the dihydrate in the QDMSO is definitely a pure form. Pure meaning that it doesn't contain any solvent molecules. And since that pattern does not match with the anhydrous pattern of the deposited structure, it could possibly be a new phase, a new pure polymorph of quercetin.
Thank you so much. Oh, we've got one more question just popping up in the chat there.
So Fatima is asking if the group space change when you change the temperature.
I'll have to check that. I cannot answer that now, unfortunately. But I'll check that, and I can come back to you if you want. I'm not sure about that now.
Mm-hmm.
Thanks so much, Panayiotis. Thank you everyone for your questions as well.